to cut it here because we are running out of time. Thanks a lot again. Please warm hand to Alexander again. And I would like to invite another presenter today with the topic of Biomimetic Robotic System with Tensegrity-Based Compliant Mechanism. Authors are Hsieh and June-Hao from the Graduate Institute of Architecture, National Ming, Chiao, Tung University. Thanks a lot. Please, floor is yours. Oh yeah, sorry about it. We have only one mic.
Okay. Good evening. I'm Bo, and I'm so excited to share the topic of our research. Basically, focus on a biomimetic robotic system featuring a tensegrity-based compliant mechanism. Next, please. So our research problem was that we have observed several technical challenges associated with robot structures within current robotic operations. Next, please. So essentially, while traditional rigid robots have been widely used in like fabrication industries with their great ability to handle massive and repetitive workloads, they can hardly work in confined spaces or unstructured environments. Next, please. And on the other hand, soft robots, although soft robots have a great perform in ill-defined spaces, but they can they cannot carry like load-bearing tasks or be efficiently controlled. Next, please. So in fact, the lack of an integrated robotic system with efficient control strategy and adaptability was what this research aimed to address. So taking inspiration from biology, specifically the physiology of vertebrates, we set out to explore how robots could adjust their structural stiffness based on their current environment or their task requirements. So some studies have highlighted the integration of bones, muscles, and joints in vertebrates ensures an efficient trade-off between rigidity and flexibility. Next, please. Which shares a great similarity with tensegrity structures. So we took this tensegrity-based concept as the foundation of this research. So we started with a prismatic tensegrity unit, which was comprised of two triangular plates on both sides, hexagonal plate in the middle, and a tensile network arranged in a circumferential pattern. Based on the simulations, we found its ability to be actuated and be stretched when subjected to pulling force along the primary axis. And by augmentations in a linear order, the spine-like topology was then constructed, and it also amplifies its deformability. So in terms of structural performance, this tensegrity-based form provides more compliance and flexibility and efficient control and effective force distribution with a self-balancing mechanism. And the mechanism is what we're going to talk about. To achieve these capabilities in real-world situations, we have developed a rigid flex coupling, which allows tension and compression components to synergize effectively. Next, please. So basically, we utilized this structural behavior, which could be considered as a compliant mechanism. Next, please. So once applied with external forces, this form was able to undergo stress distribution and thus transitioning to a new self-equilibrium state. Much like how muscles and bones work in biological systems. Next, please. So this control strategy ensures the robot structure to achieve various movements with only 3 external cables in this case. So it doesn't require complex mechanical design in each joint comparing to most traditional rigid robots. We also built up a integrated mechatronic system to precisely control the movement of this robot structure. We used inverse kinematics to convert the physics simulations into control parameters and send these data to our mechanical setups. So through a microcontroller unit to achieve various movements. The entire system allows us to synchronize the computational and physical model with control efficiency and accuracy. So basically, each control parameter set of external tensor actuator corresponds to a specific configuration. A collection of parameters could eventually be converted into continuous movements, which was the way we manipulate this robot structure in both computational and physical environment. Next, please. So the following framework was how we planned to validate its performance and to optimize its control system. So we extract a few sets of control parameters from simulations. Next, please. And then transferred to the mechatronic implementation. As the robot navigates in the space, the sensors could collect its current data from the environment, and which was relayed back to the software, so we can have a real-time monitoring of the robot's actual position and configuration. So moreover, we had repeated this process and trained the robot control system with machine learning approach to seek an optimal control. So this methodology not only allowed us to validate its versatility, but also this helped us to figure out the cause of deviations from its desired configuration. So the experimental results showcased this robot structure's proficiency in both multidirectional and unidirectional movements. Next, please. Most importantly, the combination of different motions enabled this robot structure to perform more complex movements, such as rotation combined with torsion, or extension with rotation, bending plus buckling, etc., etc. Next, please. So our findings also demonstrated that by adjusting the control parameters within an appropriate domain, next, please, we could manipulate its stiffness and range of motions. This dexterity in switching dynamics provides more efficient control and environmental adaptability. It leveraged the advantage of both rigid and soft robot structures. The potential of this structure accentuated as we trained its control system. Next, please. We utilized the supervised learning approach so that this robot control system could gradually achieve biomimetic movements with an efficient control strategy. Next, please. So this integrated enhancement also provided the robot structure's safety and adaptability when navigating in unfamiliar or unknown spaces. So with each training iteration, the robot progressively acquired the capability for biomimetic locomotion. as presented, it can conform to obstacles or environmental changes simply by adjusting its stiffness and configurations. And what's more exciting is that these vivid movements could be achieved with less mechanical complexity comparing to most existing robotic techniques. Next, please. And we believe this advantage could benefit robotic operations in confined spaces, and also with potential applications extended to like digital fabrication or structural engineering, such as biomimetic 3D printing technology or biomimicry building enclosures. Next, please. So additionally, we found a few limitations as well. So like intrinsic material properties, such as time-dependent pre-stress loss of cables or frictions between components might cause deviations or inaccuracy. So we think these should be carefully considered for further applications. In summary, our research introduced a biomimetic robotic system, a biomimetic solution that provides versatile movements, adaptability, and a more efficient control system. So in order to explore robotic operations in more spaces like unstructured or undefined or maybe like unknown spaces. So that's it. Thanks for listening.
Thank you very much. This was really fascinating work. Thanks a lot for that. Are there any questions? Yes.
Really brilliant work, thank you. I have a few questions. One is, have you tried to check the repeatability of the work with your robot? Like, what is the error tolerance when you repeat the same operation? And I asked 3 questions maybe, and then answer, so it's easier. And have you had any like configuration or reach limits? Like with normal robots, there are so many times that specific movements, we cannot do specific movements and we need to reconfigure the movement of the robot, or there are some specific reach points we are limited to reach a certain plane. Do you have such a thing as well? And I also didn't understand, like, your whole calculations are based on machine learning, or you are optimizing with machine learning, and the initial calculations of the movement and joint configurations are based on a mathematical equation, and then you optimize it with machine learning, or it's solely based on machine learning? And what is the load limits of, what is the weight load limits of such a system? How heavy can be something attached to it, and what is its effect on the accuracy of the system? Thank you.
Thank you for your question. And the first one, I think, the first challenge in like configurations, I think one challenge in that we faced was how we optimize the control parameters for achieving movements, various movements, while can conduct with load-bearing tasks. So to address this, we employed the machine learning approach to iteratively refine the control parameters. So, but there's still a few like very sophisticated movements that this robot structure can't achieve. But compared to traditional rigid robots, it already can perform with a like, let's say, more efficient control. And as for the second question, the training process. So as I presented, we utilized a supervised learning approach. So so basically the framework is that the robotic control system can learn from repeated interactions with various environmental conditions. So we collect these spatial data and the corresponding predefined biomimetic movements during each iteration. So the system can gradually acquire the ability to move or to locomote with more natural movements comparing to rigid robots. As we all know that rigid robots can do complex movements with more joints, right? But if we add like 10 or more joints, it's not efficient. But with this prototype, we can control its movement with only like 3 continent strategy, so that it can achieve the same position or same configuration, but with a less complexity. Yes, thank you. I hope this answers your question.
Thank you very much. So you applied inverse kinematics model on the 3 axes only, or for each particular joint in your Tensegrity system? 3, only 3. Yeah, very nice. Yeah, very nice. Are there any other questions?